If I transfer 225 joules to the environment while maintaining my temperature of 98.6 degrees Fahrenheit and the environment has a temperature of 42 degrees Fahrenheit, what overall entropy change is associated with this cooling process? So in this question, I'm going to take the result of the last question and do a calculation as well for the entropy change in the environment and then combine those two to see what the overall net entropy change is for the whole thing. One could argue what the entropy changes for the whole universe based on this happening. So to do this, we're going to use the formula we've been using, and the argument that I've always said we have to make is we need to make some argument about reversible heat exchange, but we don't necessarily have to apply the same criterion to both processes. We can do each one in isolation. So when I look at me losing 225 joules to the environment, that maybe I'll write over here like that's like, we'll say that's delta S for me, and that would be equal to 225 joules, and that was negative 225 joules because I'm cooling, right? And then the 98.6 corresponded in the last problem to 310.15 Kelvin, and that gave us the result for that of minus. And maybe this time I should be a little careful with not rounding off too far here, so I'll keep a few more digits. Let's see, 455. That's at least 2 or 3 more than I'll probably need joules per Kelvin. Now, for the environment, what I'd like to do, so let's look at delta S, and I'll just put like ENV for the environment. We're going to use positive 225 joules because that's the amount of heat input to the environment in this process. And again, in our imaginations, we can say this would be reversible if the environment were in contact with another object at the same temperature, even though in reality it's not. But that would be how you would calculate the entropy change for it. And since that is a possible process, it's perfectly valid to do that. 42 degrees Fahrenheit is 10 above 32. And if you multiply that by 5/9, you actually get 5.5555 repeating. And then if you add to that 273.15, you will get 278.70, like 555 repeating. So maybe I just put that in there. And again, that's in Kelvin. And I put the whole thing into my calculator without rounding, even though I'm not going to write all that on the whiteboard here. And then when I calculate this result, I got 0.8073, and then it's like 0.036. So maybe I can round that off, maybe 2 more to, am I doing it fairly here? Yeah, 2 more. I think that's a total of 6 there, same as the last one. Want it to be fair between the two, right? Don't want them to squabble. And then if I add these two, so I'm going to look at the overall entropy change as the sum of the entropy change for me plus the entropy change for the environment. So that would mean I'd add this negative number to this positive number. And naturally, since I'm not too fond of doing arithmetic by hand, I had my calculator do this. And my calculator says 0.08, I guess based on the information given to me, maybe I should round about there. It's 818,48181 is what my calculator said. And that should be in joules per Kelvin, since that's what the two terms I added are in. And so we can go ahead and check that answer. It's interesting how it turned out to be net positive. Oh, maybe it's also interesting that the answer on the slide rounded to, that's not really 3 significant digits, is it? That's 2. Well, make sure this video stays within the physics department, I'm going to say. Don't share with departments that, I won't name any names, but that might be picky about sig figs. Don't show it to them. It is interesting, though, that it's positive, because it turns out that's going to be kind of a general idea. That's really going to be the law of entropy, also known as the second law of thermodynamics, is that for real processes that are irreversible, the net entropy change, considering all relevant entropy changes, will always be positive.